We're talking about thermodynamics. We're almost to the end here, but it's been a little bit since we've lectured last, so let's just kind of talk about sort of where we left off, I believe. So last time we talked about Gibbs free energy, I believe. So we talked about Gibbs free energy. Gibbs free energy is our delta G value. We could use the delta G value to determine whether or not a reaction is spontaneous or non-spontaneous simply by sort of the value being either positive or negative. So if delta G is negative, it means the reaction will be spontaneous. If the delta G is positive, it means the reaction will be obviously non-spontaneous in that case. Delta G, which is Gibbs free energy, as we talked about last time, is really sort of energy available to do some type of work or something like that. We saw a couple different ways that you could kind of solve for a delta G value. You could kind of use what is referred to as a delta G, not a formation. These are basically table values. And you basically can just use the balanced equation and calculate the delta G naught by taking all the delta G of your products minus all the delta G of your reactants. Again, here we would take the coefficients from the balanced equation and obviously multiply those by the values that you find in the tables. You want to make sure, as we've talked about a number of times at this point, that you do find not only what you're looking for, but also the correct state of those substances. And again, you can kind of do that. And we sort of talked about the idea of, kind of based on the information given to you in the problem as to sort of the approach you want to take. So this is definitely the approach that you would want to take if you're just really given just the equation and really no other piece of information. You would want to go to that table and sort of look up those values. We also saw sort of a delta G value that relates to delta H and delta T. And we have this guy here, which delta G is equal to delta H minus T delta S. This is obviously our free energy. This is our enthalpy value. T is our temperature in Kelvin, and S is our change in entropy sort of value as well. So this as well will allow you to obviously calculate the delta G for a reaction. And obviously, in this case, you would probably want to use this if you have some delta H or delta S sort of given to you. You could potentially use this. I guess you could potentially do delta H products minus reactants and delta S products minus reactants. But again, probably would want to stick with the above equation if you're not really given any information. Given an H and an S, again, you can sort of use this. We also talked about the idea that reminder that there are different units here in terms of this guy's kilojoules. This guy is typically joules. So there is sort of that factor of 1,000 difference between those two. And that also allows us to understand whether or not, a reaction may be spontaneous or non-spontaneous, depending on sort of the temperature we're dealing with at very sort of low temperatures. And if delta S is positive, we would have a probably non-spontaneous process if our delta H is positive as well. So, that kind of positive, negative, and those temperature relationships, we can make sort of a fairly good prediction as to whether or not our delta G will be positive or negative as a result of that. I think we also sort of finished up talking about phase changes. And so with phase changes, you can look at the entropy change that's occurring there. Again, because it's an equilibrium process as we go from solid to liquid or liquid to solid and liquid to gas and vice versa, our delta G will equal basically 0 at that point. That gave us this sort of version of this equation here. Solving for delta S would give us delta H divided by T. And again, this will allow you to calculate something like the entropy of vaporization, which is basically the entropy change that's happening at that point where we have really the phase change between liquid and gas. A reminder, as we also talked about, this should not be confused with the delta S of the surroundings, which does have that negative value in there with our delta T. So again, sort of a different application, This guy has no negative. This one obviously does. And you want to make sure you do that. Here in the bottom one with our sort of entropy of vaporization, the delta H value would be the heat of vaporization for a particular substance. And a reminder that, not everything is water. So you would want to use the delta H of vaporization for whatever substance you're dealing with. And also important is the boiling point temperature. Again, if you're not dealing with water, it would not be 100 degrees Celsius probably. So you want to make sure that you use sort of the correct value for the temperature. Any questions on any of that stuff? I think we kind of talked about last time. Okay, so we've now seen a couple different ways to calculate delta G. We're going to see obviously a couple more ways as well here.
Professor?
Yeah.
Can I ask a question about the next exam?
Yeah.
Is it going to be next week?
It is probably not going to be, I would imagine, if it's scheduled. So it will probably not be, since it will cover through 18. So my guess it will probably be moved, I would think. Probably to the following week, hopefully.
Thank you.
Yep. Other questions? Okay. So we see these couple of different ways to calculate the delta G value. Here's another equation that deals with delta G, but this one is a little bit different. There's actually two on here. We'll talk about both of them here. We'll start with the top one here. This is delta G is equal to delta G naught plus RT natural log of Q. And you may be wondering, well, there's kind of like a couple of delta G's in that equation. What's sort of the difference? So one way you could kind of think about it is, this is like our delta G here under standard conditions. Again, that's kind of what they'll not usually represents in most cases. And that would be like our delta G is basically our delta G of our products minus the delta G of our reactants, like we were just talking about. R is our gas constant. It is the 8.314 version of it. T is our temperature in Kelvin. And natural log of Q. Q is the same thing that we've seen before. It is the reactant, spit that out, quotient. So that's the reaction quotient, which is basically just like we've used it before, products divided by reactants. So where did we use sort of Q before, or in these places where we kind of use Q before? It was a lot of times in those situations where we were maybe not sure we were at equilibrium, maybe initial type conditions. And that's the way you could kind of think about, why you would want to use it in this situation. It would be in a situation where you're not at equilibrium, and it would be sort of under, one way to think about it is kind of non-standard conditions, if you want to think about it. So that delta G there is sort of the delta G under sort of non-standard conditions. Remember that when we talk about sort of standard conditions, for the most part, temperature is 25 degrees Celsius. If you're dealing with any pressures, it's 1 atmosphere. If you're dealing with any type of concentrations, it's 1 molar. So something along the way here, most likely concentrations aren't going to be 1 molar. And that would be why we would use this equation up here on top. So we would calculate what the delta G would be under sort of standard conditions, table conditions, products minus reactants. If it wasn't given to you, we would use our Q, which again would most likely have something in terms of probably concentration that's not 1 molar. And then that will tell us what the delta G would be under sort of those conditions. So this is sort of, again, an equation you would want to think about as being one of those ones where, again, something not standard conditions, and you want to figure out what the delta G would be under those cases. Now, if we sort of move this guy into an equilibrium condition, a couple of things changes. The delta G there will equal 0. And we will now be at equilibrium conditions. So we're not talking about Q anymore. We're actually talking about equilibrium type concentrations. And basically rearranging that top equation gets us this one that's a delta G naught equals minus RT natural log of K. And these are all our same normal guys here. That's the obviously gas constant from above, the 8.314. That's our temperature. And obviously now that we're at equilibrium type conditions here, that is obviously the same thing really as Q as well. It is still our products, right, divided by our reactants in this case. So there's a few different ways that we can sort of interpret delta G for a reaction. Again, go products minus reactants. You could use delta H and delta S if you have that given to you. If you want to tie it to the equilibrium constant, we could do that with our minus RT natural log of K. And if we have some type of situation where we're not necessarily under perfect standard ideal conditions, we could see how the delta G value is affected by that by using the equation up there on top. Any questions on any of those there? Okay. So we'll skip this for now. But just looking at this equation here, delta G naught equals minus RT natural log of K, you know, really because it does have the equilibrium sort of constant in it, we could use what we know about the equilibrium constant to help us decide what's going to happen. So for example, obviously, if we have a large value of K, which is what this guy would represent, normally in our equilibrium constant discussion, if you have a large value of K, that means you mainly have products there. And if you mainly have products, it's probably going to imply that this reaction is going from reactants to products, which means that probably our delta G here would be a negative value to imply that it is a spontaneous process happening in this direction. Opposite is true if our K value is a small value. Our small value K means that we mainly have reactants when it's all said and done and we reach equilibrium. And that would probably mean that, you know, the reaction is basically staying on this side, which means that delta G would be positive and be non-spontaneous. Non-spontaneous would imply that the reaction is not going to head to the product side, going to kind of hang out over here basically, and we would have a lot more reactants present at that case. If we hit it with one, our natural log of K there would give us a 0 value, and our delta G would be 0. And, you know, it's sort of a toss-up at that point. You got probably reactants and products, but maybe not a lot of each sort of happening at that point. So again, because this really does relate to our equilibrium constant value, we can definitely use that knowledge that we had before to help us predict what the delta G would be and what we would expect to have at equilibrium. All right, so why don't you give one a go here, see what you come up with. Calculate the Kp for the following reaction at 25 degrees. Here's delta G value from the table that you could find. By the way, a reminder, delta G for something like O2 would be 0. Yeah, so take a minute or two, see what you come up with. We're looking for a K value here. O2 is 0, as we talked about. When you look up those kind of tables in the back of the book, for example, in those thermodynamic tables, the delta H values, for example, delta G values and delta S values are the ones we talked about. Things in their natural sort of standard state will be 0 values. We'll have a value of 0 for things of delta H and delta G. It's only delta S, which is the entropy value, that actually will have some type of number for those things. So those are the values that you typically find for things in their standard states for things like delta H or delta G. Equations and stuff like that to kind of choose from. But since we are looking for the equilibrium constant, again, that probably would be the one that we want to kind of deal with. So we would want to deal with our delta G naught is equal to minus RT natural log of K. Again, we do have R, which is a constant. We do have the temperature given to us. We are looking for this. So we do need to find our delta G naught. Again, if you have no other information given to you and you're looking for a delta G naught, that's when you would go to the table and find these values here, these kind of delta G naught of formation values. That's, again, is table pretty much where you find that. We're going to basically calculate that by taking our products minus our reactants. Remember that we do need to take the coefficient into account when we do that. So on our product side, it is O2, and that would then be 3 times 0, basically, minus our reactants, which would be 2 times the value of O3 that we would find in that table, which is 163.4. I guess I should have wrote it on the bottom there. They are kilojoules, by the way, just a reminder. And that would get us 2 times 163.4. That gets us minus 326.8 kilojoules. Any questions on that so far? And again, we did this because now that will give us really the missing piece that we need there to solve for K. So a couple things we want to think about is, again, units. So I'm going to go minus 326.8 times 1,000 to convert those kilojoules into joules. So I'm going to convert that into joules. The reason I want to do that is really because of my R value here. That is in joules. So again, remember, in these sort of thermodynamic calculations, you got a lot of things sometimes with joules, got some things with kilojoules. So you want to make sure unit-wise everybody's on the same page. Temperature there, we need to add 273 to it, gives us 298 Kelvin, and that's going to give us the natural log of K. Going to basically multiply on the right there and then divide that over to the left. And if you do all that, so 326.8 times 1,000 divided by our 8.314 and divided by our 298, basically, that's going to give us something like 131.9 is going to equal the natural log of K. To get rid of the natural, and again, that is basically multiplying these guys and bringing them to the other side. To get rid of the natural log, we need to take the E of both sides there. And when we do that, the natural log goes away there. That gives us K is equal to, in this case, looks like 1.9 to the 57 in this case. Any questions on sort of that calculation there? Now, does it sort of make sense? Well, we have a delta G that's negative, which means this reaction should be spontaneous, which means it should be heading in this direction. And that means that we should mainly have products when it's all said and done. And I would say that's a pretty big value of K there, which would imply that it's pretty much going to the right-hand side there in this particular reaction. Any questions on any of that there? So why don't you give the next one a go and see what you come up with here. In this case, we're looking for the delta G naught at 25 degrees, and we're given a KSP value, and see what you come up with in this case. To delta G, we are given a KSP value, so that obviously is an equilibrium constant. So again, we would want to use the one that had our equilibrium constant in it. It doesn't matter if it's a KSP versus a KP versus a KC. Hopefully at this point, the answer you would know is no, they're all equilibrium constants. So it really doesn't matter, what it is, as long as it's an equilibrium constant. So in this case, we pretty much have everything we need. We just got to pretty much just plug it in there. So we're going to get our gas constant. We're going to take our temperature, again, converting it to Kelvin, natural log of our KSP there, which is 1.7 times 10 to the minus 6. And going across there, that ends up getting us looks like it gets us 32,914. And these would be joules, based off of the gas constant there. Again, because delta G is typically given in kilojoules, you could convert that down into kilojoules in this case. Any questions on that there? Again, should sort of make sense. I got a positive value here for delta G. That means the reaction is not going to be spontaneous, which means it's probably hanging out over here. And if it's hanging out over here, that means I have a lot of reactants, which means I should have a small K value, which I do with my KSP. So again, all those things, do make sense. Any questions on any of that? All right, one last one here. See what you come up with. Delta G naught for the following reaction, 2.6. We got some partial pressures given to us. Calculate the delta G for this reaction and see what you come up with. Okay, so let's take a look and see how maybe to approach this one. If you're not sure, the delta G naught's given to us. We're also looking for a delta G. So that clearly is 2 delta G's, and the only equation we really saw that has that is our delta G naught. I'm sorry, delta G equals delta G naught plus RT natural log of Q. Now, how else would we know maybe this is the right one to use? It would be right here. We're given some pressures, and when we look at the pressures, again, they're not all 1 atmosphere, which would technically be sort of standard conditions. So this is, again, sort of the thing in this reaction here that's not under those sort of standard conditions is the actual pressures. Temperature is 25 degrees, which is standard temperature, but our pressures here vary. And again, that's really where we use this equation. Also kind of important, just a reminder that this is plus here. Can't tell you how many times people want to subtract that part right there. So make sure you remember it is a plus here. In this particular case, they gave us a delta G value, so we don't have to calculate it. Obviously, if we needed to calculate it like we did on the previous problem there, we would do our delta G of our products minus our delta G of our reactants. We would look it up in the table basically to do that. So they pretty much gave us everything here. Q in this case is just like we've done before. It's our products, which in this case would be the pressure of HI, and we would need to square it, divided by the partial pressure of H2 times the partial pressure of I2. So putting all this together here, looks like we have our delta G is equal to our delta G naught, which is 2.6. I, again, am going to multiply mine by 1,000 to convert it to joules because we still have the R value there that we need to make sure we don't mess up on the units. And that way we're all good in terms of the units in that case. Temperature, we're going to add our 273 to the 25. That's going to give us a 298. And the natural log of Q, so we're just going to put our numbers in here, obviously, for our pressures. So up on top should go the partial pressure of HI, which is 0.23. Again, don't forget to square it because of the coefficient that is here, divided by our H2, which was, looks like 4.26, and our I2, which was 0.024. And pretty much just got to put it all in there. And I believe in this case here, if we do that, all right, take a little natural log of that thing, times it by 298, times it by 8.314, take a 2.6 times 1,000 and add it to that. Looks like we end up with something like 967. And again, in my case here, because I did that conversion, technically would be joules. We could make it into kilojoules, which is typically what our sort of delta G is. Since it really didn't specify, you could give it an either one. It doesn't really matter in this particular case. First off, any questions on the calculation part? So what does this sort of number tell us in terms of the reaction? Which way is it going to kind of go? Well, we have a delta G that is positive, which means that the reaction is basically going to be non-spontaneous, which means it's going to hang here, which means it's really heading in kind of this direction, right, towards our reactants. We would also probably expect a smaller value of K if we were to calculate it and stuff like that. Any questions on that? Or I think that wraps up the thermodynamics chapter. Any questions on any of those things we talked about? Delta G, delta S? Okay, so that wraps up, like I said, chapter 17. We're then going to roll here into the next chapter, which is some electrochemistry. So just give me a second here. So we're off to electrochemistry here. We're going to talk about redox reactions, oxidation reduction reactions, We're going to talk about oxidation states. We'll get into really the heart of sort of this chapter, which is galvanic cells and corrosion and electrolysis. But we're going to sort of go over just some basic redox sort of reactions, how to balance equations, oxidation states, just to make sure everybody's on the same page. My experience, depending on maybe who you had for the first semester, you might have talked a lot about it, maybe not so much about it, maybe a little bit about it. So just want to make sure, again, everybody's sort of on the same page as we go through this. So we're going to kind of start with the basics and go through how to balance properly redox reactions. And then we'll get into, obviously, the galvanic cell part of it and all that kind of stuff. So, if it is a review for you, I guess that's good. If not, but hopefully, it'll help you. So electrochemical processes are really sort of redox reactions is what they're really referred to, which is oxidation reduction reactions. And when we talk about redox reactions, basically energy is released by a spontaneous process and is converted to basically electricity. And it's really based upon sort of the transfer of electrons is basically what happens in a lot of electrochemical processes. We have electrons being lost by somebody, electrons being gained by somebody. And again, those electrons, as they sort of go through this sort of circuit, if you will, helps conduct electricity. Now, when we look at a reaction like this is really a combination reaction, a synthesis reaction. This is really a redox reaction. And what happens if we look at the oxidation number, when we look at magnesium, when it is all by itself, not combined with anything, it has an oxidation state of 0. When we look at oxygen all by itself, it also has an oxidation state of 0. Magnesium and oxygen really only gain charges when they actually come together. And at that point, hopefully, right, the magnesium has a +2 charge and the oxygen has a -2 charge. So what is happening in terms of all these guys and in terms of oxidation and reduction? Well, let's talk about a couple of definitions. When we talk about an oxidation reaction, when something is oxidized, it typically will lose electrons. There's also a few other definitions that we really don't get too much involved with, but gaining oxygen as you go from reactants to products, losing hydrogen, or H2 really, as you go from reactants to products. But in most times in general chemistry, we kind of look at this aspect of it. Organic chemistry, you kind of look at these guys. Reduction, by the way, means that somebody has gained electrons. Also has sort of the opposite definition for oxygen and hydrogen. Loses oxygen as you go from reactants to products, and gains hydrogen, which is H2 usually, going from reactants to products. Again, in sort of general chemistry, we oftentimes will deal with sort of the electrons that's happening. Sometimes people remember this by the oil rig. Oxidizing is losing, reducing is gaining. Some people, like Leo the lion, goes grr. Right? Loss of electrons, oxidation, gaining of electrons, reduction. If you don't want to choose, just put Leo the lion on the oil rig. He'll go grr, and you don't have to choose any of those two. You could use them both, and you'll be fine. But really, what happens, though, when something sort of loses electrons or when something gains electrons, and sometimes people really struggle with, is it oxidation or is it reduction by looking at the oxidation states? And again, if you're not familiar with how to assign oxidation states, we will talk about that in a few slides down the road here, and you hopefully will be okay on that. But there's actually a very sort of simple way to figure out, what is being oxidized and what is being reduced. And it's just a very simple, like, number line type of deal. And usually on a number line, there's 0 there. And then on the left-hand side is negative numbers. On the right-hand side, it's positive numbers. And when things lose electrons, they become more positive because they lost electrons, got more protons. So if you find yourself just looking at the oxidation number and it is heading from, wherever it started to a more positive direction, then that guy is going through oxidation. Things that gain electrons become more negative. So if you find yourself on the number line sort of moving in the opposite direction, moving in a more negative direction here. Basically going in this direction. Then that person is going through reduction. So that's like a very super simple way, to really just kind of visually see what's happening. If something is becoming more negative, is going through reduction. Something becoming more positive is going through oxidation. So if we look at sort of this reaction here, and we look at magnesium, for example, it's going from 0 to +2. So 0 would be like in this part, and +2 would obviously be heading in this direction. So it is going to the right, which means it's going through oxidation. And we could break this reaction into what's referred to as a half reaction. And this would be the oxidation half reaction. What makes it a half reaction or an oxidation half reaction is because it is losing electrons, electrons end up on the product side when you write this half reaction. If we look at the oxygen, it's going from 0, which is like here, to -2, which is like in this direction. So it is going to the left there, and it is going through reduction. We could also write a half reaction for that, which is known as the reduction half reaction. Electrons would be found on the reactant side in a reduction half reaction. Why are they really called half reactions? Well, they're really called half reactions because when you add them back together, you get the overall reaction that's occurring. Electrons will cancel on opposite sides of the arrow, and you'll get back to your original or the overall reaction that's taking place. Any questions on that there? And that's what we see here. Again, if we take those two half reactions basically and add them back together, it gives us the overall reaction that's taking place in this redox reaction. As you might remember when you talked about different types of reactions, different ways to classify reactions, you might remember that the redox reactions were sort of a big classification reactions, and underneath redox reactions were all types of reactions like synthesis reactions, decomposition reactions, single replacement reactions. These are all basically redox reactions, but also classified in a different sort of aspect as well. Here's another example. Again, if we look at our calcium and oxygen coming together, and we again just kind of follow what is happening here in this reaction. We see that the calcium has an oxidation state of 0, again, all by itself, not combined with anything. Oxygen has an oxidation state of 0. When calcium and oxygen get together, that is when the calcium gets a +2 charge or oxidation state, -2 for oxygen. And again, if you just kind of follow that number line thing we were talking about a second ago, calcium starts at 0 and ends at +2, so it's going in the right. So it is oxidation happening there. Oxygen again starting at 0, heading to -2, which means that it is going through reduction, by the way. So again, that's just a very simple way that you can figure that out. If we split these up into our half reactions, again, we see our electrons on our product side for our oxidation, electrons on our reactant side for our reduction. When we add them together, the arrow is like an equal sign. Anything on opposite sides will cancel, and that leaves us our overall reaction that is taking place there. Any questions on that one there? Now, another thing when we talk about oxidation and reduction and things that are being oxidized or reduced, we also sometimes want to know or talk about the reducing agent and the oxidizing agent. And those are sometimes two things that people get a little bit confused upon. And let's talk a little bit about what those things are. So the oxidizing agent is always the substance that gets reduced, while the reducing agent is always the substance that gets oxidized. So when you're talking about the oxidizing agent or the reducing agent, basically it is the substance that is basically opposite of the name. And what that means is, for example, if we looked at our calcium example that we just saw on the previous slide. Calcium again going from 0 to +2 and -2. So here the calcium is being oxidized, which means the calcium here would be the reducing agent. So why is it the reducing agent? Well, when the calcium loses its electrons head over to oxygen. And by the oxygen gaining those electrons, the oxygen is now going to become reduced. So the calcium is causing the reduction of oxygen, and that is why it is known as the reducing agent. And vice versa, if we look at the O2, it is being reduced, which means it's the oxidizing agent. And it's the oxidizing agent for kind of the same reason. It's going to accept those electrons. In order for it to accept the electrons, it has to cause the oxygen to be oxidized and lose those electrons. So sometimes people get very confused when they're asked about oxidizing agents or reducing agents. So again, the simplest way to think about it is oxidizing agents, opposite of the name, is the thing being reduced. Reducing agent is the thing that's being oxidized. The real reason they're kind of named like that is, as we just talked about, that is essentially what they cause in the other species to occur. Any questions on that there? Now, what was I going to say? I don't know what I was going to say, so maybe it'll come back to me. Who knows? It's been a long week. All right, so I know it just started. It's only Monday. We'll continue on then. Now, as I mentioned before, there's also, sort of the oxygen and hydrogen definition of oxidation and reduction. And although, again, in a lot of cases in general chemistry, we don't really kind of use those often. You can. If we looked at something like this, for example, if we look at the tin from the left to the right-hand side basically has lost some oxygen, right? And the loss of oxygen means that the tin is going through reduction. And vice versa, if we look at the carbon as it goes from left to right, it gains some oxygen, and gaining of oxygen means it's going through oxidation. So you can do that. You could also just look at oxidation numbers here because you do have a metal. So this tin is +4. This tin is 0. And in that case, again, if you follow that number line, going from +4, which is over here, to 0, it's heading in that direction, which means it's going through reduction. And that's the same, obviously, definition that we get by looking at the oxidation. The good news about oxidation and reduction, as you may know, perhaps, is if you could simply identify one of those things, what is being oxidized, what is being reduced, the other substance or species is doing the opposite thing. So like in this case, if the only thing you could figure out is tin is going through reduction, by default, that would mean that the carbon had to be going through oxidation, as they always occur, together, oxidation and reduction reaction. So that's sort of the nice thing about it as well, is maybe you can't identify everything that's going on, but as long as you can figure out at least one of the things that are going on, you should be able to, really figure out what's happening with everybody else. So in this case, because the tin is going through reduction, the tin would then be our oxidizing agent. This guy would be our oxidizing agent. And because the carbon here is going through oxidation, as it says there, the carbon would obviously be our reducing agent. Any questions on that there? And I see I knew I would remember what I was going to say. So that's what I was going to say. When you're asked about the oxidizing agent or the reducing agent, they are found on the reactant side of most reactions there. So on the reactant side is really where you find those things. So for example, if you were going to be giving the oxidizing agent, you probably should give this as your answer, the whole thing, or you should give the 10 with the +4 charge. So that's how you should do it. You shouldn't just write 10 on an answer or a question like that, because, do I know you're talking about this 10? Do I know you're talking about that guy, or which one it is? So if you're asked about sort of the agents, the oxidizing agent or the reducing agent, again, should be found on the reactant side of the arrow. And you should be descriptive as to sort of which one you're talking about. Any questions on that? Okay. So how can we help ourselves sort of figure out, who's gaining and losing electrons? And we can do that by looking at what is referred to as the oxidation number. It is also sometimes referred to as the oxidation state. A reminder that when we talk about the oxidation number or oxidation state, it is not necessarily the charge that we normally associate with things. So, for example, we oftentimes will associate a -1 charge for chlorine, but chlorine could have like a +1, +2, +5, +7 oxidation state. So the way to think about it is it's sort of the charge that that element has in the way it is bound in a particular compound. So depending on how it's sort of put together with other elements and atoms as to what the charge is sort of carrying in that case. In terms of oxidation states or numbers, anything in its uncombined free state, basically all by itself, has an oxidation number of 0. So again, even though a lot of times people have that urge to see something like sodium and go, it's +1, is not +1 when it's by itself. Again, it has an oxidation number of 0. Anything that's a monoatomic ion, the oxidation number will equal the charge. So a lot of normal things like lithium is +1 in terms of oxidation number. If you had something like iron 3 chloride, the oxidation state of iron would be +3. Oxygen is -2. Oxygen is really a good place to start with, especially when you're assigning oxidation numbers, since one of the definitions of oxidation is gaining or is really gaining the oxygen, or reduction is losing oxygen. A lot of times in redox reactions, oxygen is involved. So it's usually -2. It will not be -2 though if it is actually peroxide. So if it's peroxide, it's going to have an oxidation state of -1. Peroxide is a polyatomic ion. It is this guy down here, by the way, in case you're not sure. Right there. So like obviously in hydrogen peroxide, oxidation state here would actually be -1 for the oxygen and not -2. Other than that, you almost can pretty safely roll with a -2 for oxygen when you're doing the oxidation number. Hydrogen is +1, except when it is bonded to a metal. In that case, it will come probably second in the formula, and it'll be just like in nomenclature. It'll be like hydride, which means it is -1 in this particular case. Group 1 is all +1s. Group 2 is +2, and fluorine is -1. When we add up all the oxidation numbers for a particular compound, it does need to equal the charge on it. So if something is neutral, when you add up all the oxidation numbers, it should equal 0. When it has a charge, when you add up all the oxidation numbers, it obviously should equal the charge on the particular compound. The other important thing when we do assign sort of oxidation numbers or give oxidation numbers is you need to include the charge. Yeah, so you can't just write 1. You should write +1 or -1, because obviously it could be either. And especially when you're doing oxidation numbers, make sure that you do include the charges when you do assign them. So let's take a look at this guy here. This is a little bicarbonate action happening. So when we look at this one, in a situation like this, when we do have sort of 3 things involved, you should know these rules for oxidation numbers, because you will need to assign oxidation numbers in just electrochemistry type of problems like we're talking about here, and also later on you're going to need to be able to do it when we talk about galvanic cells and stuff like that. So yeah, you do definitely need to know these rules and how to properly assign oxidation numbers. So when we do have a situation like this where we have 3 in a row and there's oxygen, again, that's a really good place to start. I would start with oxygen. It is going to be -2 for oxygen's oxidation state. There are 3 of them, which gives you like a -6 sort of overall charge. In a situation with 3, sometimes it's good to save the one in the middle for the end. So you go to the opposite side. Hydrogen is going to be +1 in this case. And if we add up everything we got going on the bottom here, that is -6 and +1, that's -5. The overall charge, though, on this guy is -1, which means it needs to equal -1. That means in this particular case, the carbon should be +4, would be the oxidation state there of carbon. So if you were to give the answer for this question, hydrogen, you would write +1, not just 1. Oxygen, you would write -2, not -6, which is a very common thing people will do, not the grand total. When you're asked for oxidation number, you're asked for just the individual sort of oxidation number of one of those guys. And for carbon, obviously, you would write +4. Any questions on that there? Okay, so why don't you try a few, see how you do for each of these guys here. Come up with the oxidation states of each of the elements and all those guys. Okay, let's take a look here and see how we're doing. So we'll take a look at the first one here. We got Li2O. So again, we do have oxygen, so a good place to start. That would be -2. Lithium, which is group 1, will always have that same oxidation state. So lithium should be +1, and oxygen here would be -2. Again, 2 of those +1s balances out the -2, gives us 0. PF3 in this case, fluorine always going to be -1. There's 3 of them, gives you a -3, which means in this particular case, the phosphorus is actually going to carry a +3 oxidation state. So fluorine -1, phosphorus +3. Any questions on that? And again, you could probably see that we normally, perhaps with, say, naming, nomenclature, and those type of things, think of phosphorus as carrying a -3 charge. But in this arrangement here, it's actually carrying a more charge of a +3 in this particular case. All right, HNO3, which is our nitric acid. So again, here we do have 3 and oxygen, so a good place to start. So oxygen is going to be -2. That's going to give us -6 overall. Going to the other side, +1. Now, in this particular case, nitric acid is neutral, which means this whole thing needs to add up to 0. And I believe in this case, then the nitrogen should end up with a +5 oxidation state. So hydrogen being +1, nitrogen being +5, and oxygen again being only -2, not the grand total, so just -2. Any questions on that one here? And again, kind of a similar idea. We normally think of nitrogen as a -3 charge, but covalently bonded here in nitric acid, it is carrying a more +5 sort of charge that's happening in that particular case. Lastly, we have Cr2O7 2-. Again, we're going to start with the oxygen, which is -2. The 7 of them gives us -14. Dichromate here equals -2 overall, which is this. There's actually, in this case, not 1 chromium, but there's actually 2. So you could do like a little math problem if you want, 2x. And if we sort of solve this out there, x would equal +6 in this case. So each of the chromiums are going to be +6, gives you a grand total of +12, plus the -14 gives you the -2 charge overall in this particular case. So chromium here, again, not the grand total, would be +6 for its oxidation state. Oxygen would be -2 in this case. Again, not the grand total either for oxygen. Any questions on how to assign oxidation numbers? It is really important, obviously, as we go through this chapter. It's what's going to allow you, hopefully, to sort of understand what is happening, for a particular substance. Any questions on that? Okay. So that's a little bit again about sort of redox, oxidation, reduction, assigning oxidation numbers. When we have a simple sort of redox reaction occurring, like for example, our one of the ones that we saw previously when we were talking about, say, magnesium and oxygen kind of coming together here, we had something like our two magnesiums plus, or actually, I'll do it this way. So, like magnesium going to magnesium plus 2, plus a couple of electrons. We have our O2 plus 2 electrons, right, going over to our O2 minus in this case. Now, when we do this, we want to make sure it's balanced. And if you remember in that equation, there was a 2 here, a 2 here. And that's why this became 4 electrons, because there's 2 magnesiums doing that. There is also, in terms of the oxygen, there's 2 oxygens, which means each one is going to gain 2 electrons, which is why we got basically to this arrangement here. But when we look at these half reactions and they're simple, you always want to make sure that the electrons on both sides are basically equal to each other before you add them together. Whenever you add a oxidation half reaction together with a reduction half reaction, the electrons should always completely cancel out. The reason for that is pretty simple. These things always occur together, which means whatever electrons are lost by something will be gained by somebody else. So when you add up half reactions together, and they're sort of simple half reactions, you basically just need to multiply maybe a half reaction by a coefficient to get everybody to the same number of electrons if they're not the same before you add them together. Now, when we get into a little bit more complicated, so for a situation like if you had, A went to A2 plus 2 electrons, and you had B plus an electron, went to B minus. If you were going to add these together, you would want to multiply, let's say, the bottom guy here by, we can get it right here, sorry, by 2. And that would give you this would then allow you to cancel out the electrons when you add them together. So sometimes you may have to multiply a half reaction by a number. Sometimes you have to multiply both half reactions by a number. But the important thing is before you sort of add back together the half reactions, they do need to contain the same number of electrons. Now, in a more complicated sort of redox reaction where we're balancing it in either acidic or basic solution, there's a few extra steps that you have to kind of go through to get it balanced. So let's talk about how to do this. And again, just to make sure hopefully everybody's on the same page. If we are going to say balance this one here, our oxidation of iron 2 to iron 3 by dichromate in acidic solutions. So the first thing you would want to start with is sort of the unbalanced equation here. And if you weren't sure what is happening in this equation, you might want to sort of figure it out. So if we look at iron here, that obviously has an oxidation state of +2. We just did this guy in the last slide. So the chromium has a +6, the oxygen has a -2. On the right-hand side, the iron has a +3, and then the chromium has a +3. So if they weren't nice enough to tell you that in the actual problem like they were here, we could use our number line to sort of figure out, what is happening, who's being oxidized, who's being reduced. The iron here is going from +2 to +3. So +2 is here. +3 is like going in that direction, which means it is going through oxidation, the iron. And if we look at the chromium here, the chromium is starting at +6, which would be like here, and it's ending at +3, which would be like going in this direction. And the chromium, because it's going to the left, would be going through reduction. So again, if you weren't sure, which one is doing which, it is kind of important to know that. It can definitely help you out as you're going through this to make sure you're not screwing up along the way. What do we do first? Well, very simply, we want to take this reaction and split it into the 2 half reactions. So 1 half reaction is the iron going to the iron. The other half reaction is, in this case, the chromium going to the chromium. And that's pretty much how you should kind of look at it. Like, you just want to take the two things that are related to each other and basically split them off into their half reactions. We have now know that this is going to be our oxidation half reaction. This will be our reduction half reaction. And while we're at it, we also know that the iron here would be our reducing agent because it is going through oxidation. The dichromate here, dichromate here would be our oxidizing agent as it is going through reduction. So again, those are a couple things that you can figure out. Once you have it split off into its half reactions, the next thing you want to do is balance the reaction, everybody other than oxygen and hydrogen. So then you want to balance it other than oxygen and hydrogen. So we balance it just like we do normally. We need to put a 2 in this case in front of the chromium, since there's 2 chromiums on the left, 1 iron on the left, 1 on the right. So we're all good in terms of that. The next thing that you want to do is, after you've balanced it, you want to then balance the oxygens. And we balance oxygens by adding water, H2O, to one side that needs the oxygen. But the problem, though, is when we add water, we're not only adding oxygen to one side, but we are also adding hydrogen to the one side as well. So to the other side, we would want to add 2 H pluses for every water we add. So the other side gets 2 H pluses to balance out the hydrogens that we added. So I'll just kind of rewrite it underneath here. So if I go, we're not going to do anything to this guy because there's no oxygen involved. Now, when we look at the dichromate, there's 7 oxygens on the left, none on the right. So the bottom half reaction there will get 7 waters to the right-hand side. Because I added 7 waters to the right-hand side, I just added 14 hydrogens. That means to the other side, I need to add 14 hydrogens. Any questions on that there? Okay. Once you have added your waters, you've added your hydrogens and oxygens, obviously by doing so, you balance out everybody else. You are now at the point where you need to balance the overall charge. So you're going to balance the overall charge by adding electrons. So if you're going to balance out this charge by adding electrons, electrons are obviously negatively charged, which means you need to add it to whichever side needs the negative charge. There's a multitude of ways you could do this, but you should really keep it simple. And the simplest way, and the way you probably won't screw it up, is to just very simply look on the left-hand side of the arrow, add up all the charge, and look on the right-hand side of the arrow, add up all the charge, and then add your electrons to whichever side needs it. They do not have to equal 0 on both sides, but they do need to equal the exact same charge. So if we look at the top one, +2 on the left-hand side overall, +3 on the right-hand side overall, that means the right-hand side here should get 1 electron. +3 and -1 is +2. +2 on the left-hand side. Is that good where I added that? It is, because earlier I figured out that that is my oxidation half reaction, And that means my electron should end up on the product side like it did. So that probably means hopefully I didn't screw up at this point. We do it on the bottom. I got 14 positives for the H's on the left and a -2 for the dichromate. That's a +12 happening over here. Right-hand side, that is a +6 happening here as water is neutral. So the left-hand side here will need 6 electrons. 6 negatives and 12 positives gives me a +6 to match the +6 on the right-hand side. Also makes sense because we know that that second reaction is a reduction reaction, and my electrons should end up on the left-hand side of the arrow. When you add electrons, and if you end up adding them to the same side of the arrow, you screwed up. Yes, they should always end up on opposite sides of the arrows because one is losing electrons, one is gaining electrons, so always opposite sides. And again, understanding which one's your oxidation and reduction could help you make sure that you're adding them to the correct side. Any questions on that so far? All right, so the last thing to do at this point is we want to add them together, but before we could add them together, we need to make sure we have the same number of electrons there in each half reaction, and then you could add them together. So if we look at the top half reaction, we only got 1 electron. If we look at the bottom half reaction, we have 6 electrons. What that means is we need to multiply the top reaction by 6, the entire reaction by 6. So what I'm going to do is I'm just going to rewrite on the next page just so I got somewhere to write. So I'm going to take 6 times that top reaction, and that would give me 6 of the iron 2 goes to 6 of the iron 3 plus my 6 electrons. The bottom reaction I didn't do anything to, so I'm just going to rewrite it. And again, the top reaction, I multiplied everybody by 6. At this point, I now have same number of electrons on each side. We could add these reactions together. We're going to cancel out whatever is the same on opposite sides of the arrow or reduce it down. In this case, that looks like it. So that's going to give me 14 H pluses plus Cr2O72 minus plus 6 iron 2. Everything on the left-hand side of the arrow stays on the left-hand side of the arrow. Everybody on the right-hand side of the arrow stays on the right-hand side of the arrow. 6 iron 3 plus 2 Cr3 plus 7 waters. And if I did not screw this up, this should represent the balanced redox reaction, and it should be balanced in 2 ways. It should be balanced like a normal reaction. Got the same number of elements on each side, so that's 14 hydrogens on each, 2 Crs on each, 7 oxygens on each, and 6 irons on each. And it should be balanced by overall charge. Overall charge on the left is plus 14 and minus 2 is plus 12. And that's 18. That seems like a lot there. That's 12 and 12, 24 plus 24 on the left, 18 on the right there, and 6 more gives me plus 24 on the right. So balance both in terms of numbers of elements and charge on both sides. Any questions on that there? This would represent our balanced equation in acidic solution. What if we needed to do basic solution? And again, if we needed to balance this in basic solution, what we would do is, and again, there's a few different approaches you could do this with, but the simplest approach, if we were doing this in basic, is to do everything we just did, to just basically balance it in acidic solution. Don't worry about the basic part of it. And what you would end up with is this equation like we have above. And once you've balanced it in acidic conditions, Now to really turn it into basic, you're going to basically add OH minus to both sides. And the amount of OH minus that you add is equal to the number of H pluses you have in your acidic solution. So if we look at our equation here, I have 14 H pluses on the left-hand side. I would then add 14 OH minuses to both sides. So again, OH minus added equal to the number of H pluses. And that is because when we take OH minus and H plus together, that will now make 14 waters on the left-hand side. Everything else here will remain the same. Now, what we could typically do at this point is I got 7 waters on the right. That will reduce down to make this 7 waters on the left. And at that point, you probably should be done. And this equation here would represent the balanced equation in basic conditions. And it should still be the same balanced. So if you go through and you count everything up here, 14 H's on the left, still 14 on the right, 2 CRs, 2 CRs, 7 oxygens, and 7 more make 14 on the left and right, 6 iron on both sides. Grand total of charge is plus 10 on the left. And I believe what we got there should hopefully be plus 10 as well. So that's 18. And 6 is 24, less 14 is plus 10 as well on the right. So this would represent it balanced in basic conditions. Any questions on how to balance a redox reaction? How do I know this is balanced in acidic conditions? Well, I see H plus, right? So that screams acid conditions. How do I know this is balanced in basic? I see OH minus in the final formula. That tells me it's basic. So, you know, these are the things that you typically would sort of see in there. Any questions on balancing these equations here? All right, we will lay it up there for today.